are not both 0. It can be a less than symbol, or less than or equal, or greater than symbol, or greater than or equal. Okay, so we're going to learn how to sketch the graph of a linear inequality in 2 variables. Okay, the easiest way would be to go right into an example. Okay, for our first example, we will sketch the graph of the inequality 2x plus y is less than or equal to 4. By this I mean we would like to find the set of all points in the plane whose coordinates satisfy this inequality. To start, 2x plus y less than or equal to 4. We will start by sketching the graph of the corresponding line 2x plus y equals 4. This line will serve as a boundary for the solution set. Okay, now to sketch a graph of this line, we would need 2 points on the line. We could get the intercepts. For example, we could set x equal to 0, and if x is 0, y is 4. We can set y equal to 0, and if y is 0, 2x equals 4, or x equals 2. We now know 2 points on the graph, this line. Let's plot them. We have 0, 4, and 2, 0. Connecting them by a straight line. Okay, we have now 2x plus y equals 4. Now, as I mentioned before, this straight line, it's supposed to be a straight line, is going to be a boundary for the solution set. If the original inequality is of the form less than or equal or greater than or equal, we draw the line in with a heavy line. And the line will be part of the solution set. Okay? If it's a strict inequality, that is either just a less than or a greater than, we will draw the line in as a dotted line to indicate that the points on the line themselves, those points are not part of the solution set. All right, now the set of all points in the plane satisfying this inequality, okay, will consist of all the points on this line plus all of the points on one side of this line, and we have to determine which side. Okay, now there are 2 ways of doing this. One way is to say that 2x plus y equals 4 could be written in the form y equals minus 2x plus 4. And in fact, the original inequality could be written in the form y is less than or equal to minus 2x plus 4. In this way, we can see that y equals minus 2x plus 4 represents this straight line here. And we're interested in all points so that y is less than or equal to minus 2x plus 4. For the y equals minus 2x plus 4 part, we have the actual line. Now the points such that y is less than minus 2x plus 4, okay, the y value in that case would be less than the y value of the line, and the points would fall below this line in this region in here. If this is y equals minus 2x plus 4, this region down here that I've shaded in would be y is less than minus 2x plus 4. The region above the line would be y is greater than minus 2x plus 4. Okay? This is y is greater than minus 2x plus 4 because the points here have the property of the y value is greater than the y value of the line, so they're above the line. Here we have y equals minus 2x plus 4, the line, and then underneath y is less than minus 2x plus 4. So if we're interested in y is less than or equal to minus 2x plus 4, that means we want the line indicated by the heavy line rather than a dotted line, and all the points underneath. So we have shaded in the solution set. Okay, the other way of doing this would be to start with the original inequality, 2x plus y less than or equal to 4, and as before, sketch the graph of the corresponding line where we replace the inequality symbol by the equality. Start exactly the same way we did before. And we know from before that the intercepts were 0, 4, and 2, 0. Once again, that is the line 2x plus y equals 4. Now, we're trying to figure out which side of this line we should include. In other words, which side of the plane, which portion of the plane should be included in the solution set. What we can do is simply take any point that is not on this line and use it as a testing point. Very often, we use the origin as a typical testing point. Okay, we're interested in using 0, 0 as a test point. And we want to see if 0, 0 makes the original inequality a true statement. If it does, that would tell us that 0, 0 is on the correct side of the line. And all points on that side of the line would be part of the solution set. Let's see what happens. Using 0, 0 in here, we'd get 2 times 0 plus 0. Okay, is this less than or equal to 4? Is 2 times 0 plus 0, is 0 less than or equal to 4? Yes. Which means that 0, 0 is on the correct side of the line. Okay, so we took this point, which is over here. We saw that when you substitute in 0, 0, we do get a true statement. Therefore, 0, 0 should be on the correct side of the line, and all points on that side of the line would be part of the solution set. So we have the line and all points underneath it. So either way, either solving for y and figuring out that this means y is less than or equal to minus 2x plus 4, meaning we want all points on the line or under the line in this case. If it had been greater than or equal, we would have wanted all points on the line or above the line. Or just taking any point that is not on the line. Okay, and whenever 0, 0 does not fall on the line, I usually use that as a testing point. Substituting it in to the original inequality. If you get a true statement, then the testing point is on the correct side. If it had come out that it was not a true statement, then 0, 0 would not be part of the solution set. I would know that this portion of the plane is not the solution set, then this portion must be. Okay, let's try by sketching the corresponding line, 2x plus 3y equals 12. Making a simple table of values. And once again, I'm going to be using the intercepts. If x is 0, 3y equals 12. Y is 4, is a point on the line. If y is 0, 2x is 12, x is equal to 6, is also a point on the line. So the line goes through 0, 4, and 6, 0. 0, 4, and 6, 0. Okay, now since this inequality is a strict inequality, it's not greater than or equal, just greater than, I am going to dot in the line. It's still going to be a boundary of the solution set, but the points on the line themselves will not be part of the solution set. Okay, this represents 2x plus 3y equals 12. Okay, now let's just try a testing point to see which side of this line is our solution set. Okay. Our test point is 0, 0 once again. I can use it because 0, 0 is not on the line. If the line went through the origin, I would just pick any other point in the plane that was convenient to use. Okay, now we go to the inequality, 2x plus 3y is greater than 12. And we see if the test point gives us a true statement. Okay, 2 times 0 plus 3 times 0 greater than 12. Is that true? Is 0 plus 0 greater than 12? No. Okay, so the test point, 0, 0, is not on the correct side of the line. The solution set would be the portion of the plane, Okay, with a line as a boundary that does not include 0, 0. Once again, we tried the test point. We substituted in 0, 0, and we found out that we did not get a true statement. In other words, 0, 0 was not part of the solution set. Neither is any point on this side of the line, the same side of the line as 0, 0. The solution set consists of all points in the shaded in region in there. Okay, the line is a boundary, but the points on the line are not included. I just want to bring you back to the preceding example. Once again, we replaced the inequality by an equation. We sketched the line. We tried 0, 0 as a testing point, but when we substituted in the 0, 0, we got a true statement. 2 times 0 plus 0 was less than or equal to 4. Since that was true, okay, 0, 0 was part of the solution set, and so were all points on that side of the line. All right? Back in this example, when we tried 0, 0, we did not get a true statement. 2 times 0 plus 3 times 0 was not greater than 12. Therefore, 0, 0 was not part of the solution set, nor was any point on this side of the line. Therefore, the solution set consisted of the points on the other side of the line. The dotted line, once again, indicates that it's a strict inequality. The points on the line themselves are not part of the solution set. For our next example, we will sketch the graph of the inequality x is less than y. Once again, we start by graphing the related equation, x equals y. We need 2 points to determine the straight line. As before, if we try for the intercepts, if x equals 0, then y equals 0. If y equals 0, x equals 0. Okay, the only intercept is the origin, and therefore we'll need some other point. Any other point would do. For example, we could let x equals 1, then y would be equal 1. Okay, or x equal to 2, y would be equal to 2. So if the line goes through the origin, well, that's one point, and then you just pick another point. Okay, if it doesn't go through the origin, the 2 intercepts can be used to sketch the graph of the line. So we have 0, 0, 1, 1. Okay, the line, which I will dot in because this is a strict inequality, looks like so. That's the line y equals x or x equals y. Okay, now we need a test point. However, we can't 0, 0 is on the line. So we'll use any other point. Okay, that is easy to see. For example, we could use as our test point 3, 0. Just pick that, some point that was clearly, or it's easy to see on one side of the line. Okay, we use 3, 0 as a test point, and we see what happens here. We substitute into the inequality x is less than y, and we say when we do that, is 3 less than 0? X equals 3, y equals 0. We're substituting into this inequality. Do we get a true statement? No. Therefore, 3, 0 is not on the correct side of the line, and the solution set must be the region in here. We tried a test point that was not on the line. 0, 0 could not be used since the line went through the origin. Okay, so we tried some other point, 3, 0. Could have used any point at all. I wanted something that, was clearly on one side or the other. So 3, 0, we substituted in. We see we did not get a true statement, so 3, 0 is not part of the solution set, nor is any point on this side of the line, so the solution set is up here. By the way, we could have also done this the other way. We can realize that if x is less than y, this is equivalent to saying y is greater than x. Okay, x is less than y, or equivalently, y is greater than x. Remembering that this is the line y equals x, the points above the line here have the property that their y-coordinate is greater than their x-coordinate. The points below the line have their y-coordinate less than their x-coordinate. So that would have told us that y greater than x or x less than y is above the line. Okay, for our next example, we will sketch the graph of x greater than or equal to 1. Remember when I started off, I said any inequality of the form, say ax plus by less than c or less than or equal to c, greater than or equal, where a, b, and c are real numbers, and a and b are not both 0, but either a or b might be 0. And in this case, we have the x term, the y term rather, has dropped out. Okay, our procedure is still the same. We will graph the related line, x equals 1. X equals 1, of course, we recognize to be a vertical line, okay, parallel to the y-axis, 1 unit to the right of the y-axis. And because this is x is greater than or equal to 1, we will use a heavy line to graph x equals 1, because the points on this line will be part of the solution set. And we could use a test point. Actually, common sense tells us that here are the points whose x-coordinate is greater than or equal to 1. But simply using 0, 0 as a test point, the inequality is x greater